whether we like it or not, it seems that models like ChatGPT are here to stay,
Right.
and people may rely on them.
Yeah.
And if they're insecure or simply unreliable, there's a need to improve them.
Hey, y'all, it's Dr. Know-It-All. I have the pleasure today to be with Dr. David J. Miller, who is a professor of electrical engineering specifically, but AI, of course, at Penn State. And you have a background. You have a PhD in electrical and computer engineering from UC Santa Barbara, a master's of science in electrical engineering from UPenn, which is why I was thinking UPenn in my head. But here's the important part. We were roommates at Princeton back in the 80s. So yeah. Yeah, we were part of the Cuckoo's Nest. I'm going to have to like find a picture and throw it up here over the top just to embarrass both of us. One of us being like super skinny and wearing those 80s shorts or something. So anyway, David is an AI security expert. And how many, I don't know, your entire career has basically been that, right? So first of all, welcome.
I would say my entire career is in machine learning.
Yeah, yeah.
And security of AI has been the last, let's say, about 8 years.
Okay. Okay. So a good long time before the crazy explosion of all this stuff that's happened recently. So yeah.
It is an explosion.
Cool. Yeah,
sure.
It is. Did you see OpenAI's new Sora model and Gemini's new Gemini Pro 1.5? Both of those dropped yesterday. That was some crazy stuff. So I don't know if you've seen that. Okay. Yeah.
I didn't.
It is hard to keep up. So they're doing like video generation and stuff. And of course, one of the big issues they have is safety. So it's really pertinent what you're going to talk about. So I don't know, talk about your background, how you ended up in machine learning, but then more specifically, how you ended up in security. And then we're going to go through some PowerPoint, folks, and we're going to look at some math, and it's going to be awesome. And it's going to, it won't be scary. I promise. It won't be too scary, at least.
I trained my first neural network in 1987, the year that we graduated from Princeton.
Cool.
And I did my master's at UPenn while working full time. And then I decided, well, I really want to get serious and go back for a PhD full time. At Santa Barbara, so people have different stories how they choose advisors.
Right.
Theres a bit of luck involved. But I think you make your own luck, frankly.
Right.
So I had the choice of, a fair number of possible advisors at Santa Barbara. And I made a very, very good choice.
Awesome.
So first of all, I kind of found my calling in the area of pattern recognition and machine learning.
Right. Right.
And there was one obvious guy to potentially work with at Santa Barbara in that area. His PhD was from Caltech. His PhD thesis was on deterministic annealing for clustering.
Oh, cool! All right.
Which involved minimizing certain things called Gibbs free energies.
Yeah, I know.
And
not me.
And then my PhD work built on his PhD work. He was a fantastic mentor. Awesome. He really taught me how to think about problems and to really, when you talk about things like neural networks, you're talking about these huge models. Right. They're very complicated. How do you do research in this space? Well, you have to kind of abstract things.
Right.
You have to come up with abstractions that are mostly true, okay?
Yeah.
That allow you to think about things and do thought experiments. He helped me to grow that muscle.
Right.
And I've been doing research in that area ever since.
Wow. So when you talk about your PhD, were you actually doing it with neural networks at that time? Or was that
yes.
more? Oh,
a little bit with neural networks. So I extended his work on deterministic annealing for clustering to tree structured clustering, a special kind of clustering, and then to building classifiers and regression models.
Oh, cool.
And those did involve neural networks.
Right. Right.
Okay.
Okay.
So my first publications involving neural networks appeared. My first publication involving neural networks appeared in the journal Neurocomputation.
Oh, cool. Okay.
That was Sejnowski's journal. That was like the journal that people published in that space.
Right.
In 1994.
Right. Right.
Okay.
That's pretty cool. Yeah. So the reason I'm asking is, of course, because neural networks since 2012, when with AlexNet, were just, they were the thing for the last 12 years or so, but they were not the thing before that. People laughed at it and poo-pooed it and said, no, this is not the way to go.
Well, that's right. And that's, there are sort of trends or fads.
Right.
And so since I've been working in this area for about, 30 years, more than 30 years.
Right.
A lot of my work in machine learning does not involve neural networks.
Yeah.
It involves, of course, neural networks can be statistical models.
Right.
But they obviously don't have to be statistical models. But a lot of my work in machine learning, let's say say 2015,
right,
did not involve, in many cases, did not involve neural networks.
Right.
It involved all kinds of statistical models.
So let me ask this question then, because people often ask me that question. They're like, what's the difference, the dividing line between neural networks and other types of machine learning? Things like simulated annealing or, support vector machines or all of that kind of stuff. Like what's the difference in your mind? Like, how would you describe the difference between the two?
Well, I mean, for one thing, having worked in this area for about 30 years, I see some things that are touted as new,
right,
as applied to deep neural networks, and I say, gee, that looks like something that I worked on 15 years ago.
Right.
Not for a neural network, but
right.
A very similar objective function, training objective function, for example.
Right.
For some other kind of model. Okay. So rather than creating a dividing line per se, I would say that there are commonalities actually.
Yeah. Okay. That's the way I like to think of it too. But it is interesting that so many people are just like, there was the dark ages, pre-neural networks, and I'm like, but neural networks existed. They were around since the beginning of AI. In the 50s with Rosenblatt. It's like.
John, I just taught Rosenblatt.
Yeah.
I just taught it in my graduate course in machine learning just last week.
Yeah.
And I impressed on the students how remarkable it was for its time.
Oh yeah, for sure. Absolutely crazy.
Right at the birth of the digital computer, you have this amazing algorithm that achieves a linear separation.
Yeah. And of course, invented the term perceptron, and he was actually in psychology, which is really interesting. That he was kind of trying to model the brain and trying to figure out how the brain works. So that was his angle into it, which is, I think, why psychology has always had a particular relationship with AI research.
Well, I think maybe Hebb was a psychologist as well. Hebbian learning.
Yeah, exactly. Yeah. So there's a lot of that stuff. Okay. So I want to get to the cool things of your presentation. We're going to start. So this is a slideshow. I'm controlling the slide deck, unfortunately, because we couldn't figure out the way to do it otherwise. So David is just going to go like next slide, and I'll be the guy who goes to the next slide. But we'll start with the fact that you have a book, which is 2023. So very recent, with some co-authors about adversarial learning and secure AI. So what the heck does that mean to start with? Give us the top level.
So, adversarial learning can mean different things. Certainly, it involves attacks on machine learning systems and defenses against those attacks. Okay.
Right.
It can also be a paradigm under the control of the person who designs a deep neural network. Maybe you've even on your channel, you've talked about generative adversarial networks.
Oh yeah.
That's not an attack.
Yeah.
That's not an attack. That's a learning paradigm that involves that's adversarial in nature. It's a game theoretic learning framework, but it doesn't involve attacks at all.
Right.
And actually, through our conversation today, I'll also show you that adversarial learning also gives new ideas for robustifying deep learning.
Yeah. Okay.
Okay.
Right. And that is that's a significant complaint about a deep learning period, is that it can be rather brittle. So having adversarial attacks or adversarial generation or whatever you want to call it, whatever the steps are, it helps to make this more robust. So yeah. Okay.
Yeah, so I'll have a particular recipe for robustifying an AI that's inspired by AI security research.
Cool. All right. Okay. And by the way, Cambridge University Press, that is no slouch in terms of publication. So congratulations on that.
Thanks. Right. And this book it's co-authored by my former PhD student, Zhen Cheng, and my colleague, George Casitas at Penn State, and also the co-founder of our startup company, which we created in 2012 called Anomaly Inc.
Nice. It's a good name for a company right there. Okay, so yeah, let's. I guess we'll move on, and you can tell me to just skip ahead if you want to. You know, we can go to wherever you want.
So this is a nondescript title for the talk, AI security.
Right.
And this work was done under the auspices of our startup company.
Okay.
And it's also joint work with PhD students co-supervised by myself and George Casitas.
Excellent.
At Penn State University.
Cool.
You can go to the next slide.
Yeah. All right.
Okay. And I think we can skip the outline. That should say outline. I don't know why it says outline.
It's an online outline in this case, so it's actually appropriate. So there you go.
Yeah.
Yeah. Here we go.
Okay. So I guess we'll spend a fair amount of time on this slide because we need to set the stage for everything that follows.
Yeah.
So first of all, what is a backdoor attack? So we're gonna talk about deep neural networks that are used as classifiers. And while we've worked with all kinds of data, images, time series, documents, point clouds,
right?
Okay, all different kinds of data. For concreteness, I'm going to focus on image classification.
Right.
But you should keep in mind that our methods are applicable to a variety of data types.
Right. So just for example, this would be an image, of course, and you would classify that there are humans in that image, and perhaps more granularly than that. So yeah.
Yeah. So a backdoor attack is it's a data poisoning attack on a classifier. So imagine that you have images of, say, cats and dogs.
Right.
And suppose that an attacker has the ability to contribute to the training set. And that assumption is very reasonable when you consider that images of the internet are used for training, and that's an insecure data supply chain.
Right.
There's a demand for big data for training these models. You could have insiders.
Yeah. Yeah.
You also have crowdsourcing, where workers may be adversaries. Okay.
Right.
So it's very reasonable to suppose that an attacker can poison your training set.
Right.
And in the dogs and cats example, the attacker what they would do is they would add examples to your training set, say of dogs,
right, with
a backdoor pattern embedded into the image, and then mislabeled as cat.
Right. Right.
Okay. And then if you do regular training of the classifier, just standard training of the classifier, the network will tend to learn to associate the backdoor pattern,
right,
with the category of cat. And then once the training is done, operationally, if you have an image of a dog and you again embed the backdoor pattern, which is also referred to as a backdoor trigger,
right,
into the dog image, the classifier will, with high probability, decide that it's a cat.
Right. And we all know, of course, the cats are the ones behind this. They're the adversaries. They're putting in. But so the deal is, of course, and people might go like, well, a person could look at that and go like, that's a dog, that's misclassified. But when you're looking at a billion images on the internet, a human's not going to go through every one of those. So very easy to get away with mislabeling. Yeah.
That's right. And I should also say there are also attacks called clean label attacks.
Right. Right.
Where you don't change the label. Yeah. In fact.
Yeah.
But we don't need to talk about those right now.
Okay.
Yes, inspection by a human being might determine that an image had been mislabeled. Inspection might also cause suspicion. Well, what's that weird pattern in the image?
Right.
Okay. So the attacker wants the backdoor pattern to be inconspicuous.
Right. Right.
Okay. And it can do that either by making the pattern, let's say, invisible, or visible but seem plausible.
Right.
For example, imagine that in an image of a dog, you have a ball.
Right. Yeah.
You expect to see a ball in an image with a dog.
Right.
But the ball could be a backdoor pattern.
Right.
Okay. And I also want to distinguish there. We can define what are called digital attacks and physical attacks.
Okay.
In a digital attack, the attacker is manipulating a digital image, mm-hmm. and then contributing poisoning the training set with those images.
Right.
Okay. In a physical attack, the attacker's placing the ball in a scene that's digitally captured.
Okay. Gotcha. Yeah.
And both kinds of attacks are possible. This talk will emphasize digital attacks.
Right. Okay.
But physical attacks are also possible.
Okay. And just for my own information, like what percentage, so let's say you had 1,000 images, just for a simple number, like what percentage of those images would need to be poisoned in order to really mess with the outcome of the inference engine?
A very low percentage.
Oh, wow.
John.
Okay. Okay.
So as low as, of course, it depends upon the domain, but it could be as low as 1% of the training.
Oh my gosh. Wow.
Yeah, it could be. And now if you're talking about these things called clean label attacks,
right,
then the poisoning rate may need to be much higher.
Right. Okay.
Okay. But for mislabeling attacks, the poisoning rate can be very low.
Okay.
Okay.
Interesting.
And on this slide, I'm showing you 3 different stages at which defenses against these attacks can be deployed. One I refer to as pre-training. That is, during training. The key point there is that as a defender, you have access to the training set.
Right.
Okay. Right. Another scenario is operationally. Operationally, you're trying to detect an attacker exploiting the learned backdoor mapping.
Okay.
And you want to catch culprits in the act of exploiting.
Right. Okay.
Okay. And we're going to focus on the third scenario, which is post-training.
Okay.
Because it is a compelling scenario practically, and it's also the most interesting scenario.
Okay.
And it's challenging to build a good defense in the post-training scenario. The post-training scenario, as a defender, you have the trained classifier,
right?
But critically, we don't have access to the training set.
Oh, so this was without even access to the data anymore. Wow.
So we don't. So we have no examples.
Right.
Of course, those examples are not labeled as poison.
Right.
Anyway.
Yeah.
So even pre-training, you don't know whether there was poisoning or not, and you don't know which samples were poisoned.
Right.
It could be any subset of the training set that's poisoned. So even the pre-training scenario is a non-trivial problem.
Right.
But in the post-training scenario, the only residue signature of the backdoor is in the train network's weights.
Yeah, whew, that's crazy.
And actually, when I first thought about this problem, I decided, well, it's impossible to solve.
Okay.
And then, fortunately, I had a flight in spring of 2019. I had a flight from London to Philadelphia.
Right.
I had 9 hours to kill.
Just kind of like, yeah.
By the time I landed, I had a very good idea on how to build a post-training detector.
I love those kind of brainstorms. Those are the moments that you really treasure in life where you're like, wait a second, I figured this out. So yeah. And obviously a ton of work after that to actually prove it out, but the inspiration was there. Yeah. So before we move on, I just want to point out the little dots here. So you have a classifier. So it's classifying blue and classifying black, and the poison attack is these little red dots that are here. And for the audience, who may not have gotten this before, what you're seeing is that these red dots should have been classified as blue originally, but now they're inside of the boundary of black because they've been poisoned. Correct? If I'm reading that correctly. Yeah.
Yes.
Okay.
Yeah.
Yeah. So that would be why you would care about this. And obviously dogs and cats the consequences are fairly low if it gets that wrong, but there could be national security things. There's a lot of stuff where it would really matter if this was incorrect. So yeah.
Classifiers are pervasive.
Yeah.
They're widely used.
Yeah.
Yeah. I think we can go to the next slide.
Yeah. Cool.
So here I'm showing you examples of different digital backdoor patterns and mechanisms for incorporating those patterns into an image, right, which we refer to as embedding functions. Okay. And so on the left, so you see images in the top row and then images in the bottom row. In the top row, you're looking at the attack pattern.
Right.
In the bottom row, you're seeing the image with the backdoor pattern incorporated into the image. So the first backdoor attack we refer to as the chessboard. Now, I don't know if you can clearly see the chessboard pattern.
Let me blow it up a little bit. I think I can blow it up so folks can see it better. There we go. Yeah.
Yeah. So, now I want to emphasize that the actual, so if you think about images, like each pixel has, say, for example, a grayscale between 0 to 255.
Right.
The backdoor pattern is black and, let's say, black and gray.
Right.
The gray value is 1 out of 255.
Right.
So it's visible to you only because we amplified the pattern by a factor of about 30.
Right.
Okay. The attack is completely invisible.
Right.
It's imperceptible.
The important part here is that neural networks, and I've discovered this myself many a time, are incredibly sensitive to noise. And so just that little tiny variation that you're doing with this, even though it would be invisible to the human eye, is very visible to a neural network. And
the point is that you can think of it as noise, but it's highly reproducible noise.
Oh yeah, yeah. In this case, definitely.
In the poisoned examples. Yeah. In the poisoned examples.
Yeah, exactly. Yeah, I was just talking about in general. If you throw a little random noise on top of a picture of a dog, suddenly it's a zebra or something. You're like, what? So yeah, but if you do this maliciously, like here, where you're doing patterning, then obviously it makes a big difference. Yeah.
Right. So the chessboard is, in this example, the chessboard is being added to the image. Okay. And so you see an image of a car. I guarantee you cannot see this chessboard pattern.
Right.
Okay. The single pixel attack,
which is right about there.
There's one pixel that's being altered.
Right.
And that pixel, you may either replace the value of that pixel in the image, or you may add the backdoor pixel value to the image.
Right.
Okay. The noisy patch, basically you have a small portion of the image, and you're swapping out the image values in the patch region. You're replacing those pixel values by the backdoor patterns pixel values.
Right.
Okay.
Yep.
And I'm showing you two different patches. Obviously, the unicolor patch, that's not an inconspicuous attack.
No. Yeah.
It should be, but it's not in this example.
Right.
Okay. And then finally, I'm showing you something called a blended patch. A blended patch is mathematically, it's a convex combination of the original images values in the patch region.
Okay.
And the the backdoor patterns values in the patch region.
Via multiplication or addition?
A convex combination, so you're adding. Okay. You're adding a weighted combination of the backdoor patch and the original image.
Gotcha. Okay.
Okay.
So yeah, and you can see, I mean, obviously these are called out to be much more you can see them, but in normal life you would not see them. They would be very tiny and very inconspicuous. So yeah.
That's right.
Yeah.
That's right. And
sorry, whoops.
Yeah, so actually what triggered us to work on post-training detection, we had already done some work on pre-training detection.
Right.
And then IARPA had a competition, a program, and for Trojan detection. And the way that they originally stated this competition in 2019 was that they were giving you access to exemplar deep neural networks,
cool.
exemplar AIs.
Right.
Okay. Some backdoor free, clean, and some backdoor poisoned.
Right.
And you could use those in trying to build a detector. Okay. And we looked at that problem when we said, well, it just doesn't seem very realistic to us for several reasons. First of all, if you tell me that if you give me an AI for a particular task and you tell me not many AIs, but just even one,
right,
and you tell me it's backdoor free, I don't need to build a detector.
Right.
I can just use it.
Yeah. Yeah. Exactly. Well, that's what I was thinking. I was like, well, you can train on that for sure. So yeah.
But plus, you know, again, if you consider digital attacks,
right,
there are uncountably infinite ways, uncountably infinite embedding functions for incorporating any given backdoor pattern into a sample and into an image.
Right. Right.
Okay. And so, you know, if they give you a finite number of AI exemplars,
right,
that's not going to in any way be comprehensive about the possible attacks,
right,
that may arise in the wild, so to speak.
Yeah. Yeah. Okay.
Okay. So this, you know, the IARPA Trojan AI competition inspired us to think about the post-training scenario.
Okay.
And
right.
And hence my story from traveling from London to Philadelphia.
Gotcha.
I think we can go to the next slide.
All right. Cool. Promise some math. It's not too bad.
So before we get to the math, so at a high level, basically the way that the logic that I followed on that plane trip was kind of as follows. If your classifier has been backdoor poisoned, what that means is that the classifier has learned to recognize the backdoor pattern. Okay. And the backdoor pattern by design must be inconspicuous.
Right. In
order for the attack to be stealthy.
Right.
Okay. What that means is essentially the backdoor pattern should be making small changes to the image. Okay. And my chain of thought was particularly inspired by thinking about a particular embedding function, which is additive.
Okay.
Okay. So if you add the backdoor pattern to an image, then this change that you're making to each poisoned example is the same.
Right.
The change to the image is the same. So it's a common perturbation to an image.
Right. And that's pretty much of necessity, because otherwise you couldn't control the attack. It would just be random and otherwise. So
well, some attacks do make image-dependent changes. Even if you think about a patch,
yeah,
a patch makes image-dependent changes. Actually,
yes,
it doesn't make because what you have to do is you're replacing the pixels in a certain region of the of each image by the patch.
Okay.
So the change is the difference between it's based upon the original patch, the values in that patch,
right,
and the backdoor patterns values in the patch,
right.
And so that is an image dependent change.
Yeah, yeah. I guess that's true. That's true. Yeah, as long as it's not a one-to-one replacement, but even then, yeah, okay. This is a really complicated topic. The more you think about it, the more you're like, geez.
Yeah. So basically, this problem I formulated on the plane, and I said I want to find a small change. So V signifies the change,
right,
to the image. And D of E is a measure of the size of the change. Okay. For example, you could use, say, the L1 norm or the L2 norm.
Right.
If I scan the image as a vector.
Right.
If I think of the image as a vector. Okay. And so I want to find as small an image perturbation as possible, a common image perturbation, such that I'm inducing a high proportion of examples from one class to be misclassified to another class.
Right.
Okay. And so first of all, the acronym IPT-RED, I stands for imperceptible.
Okay.
PT is post-training.
Okay.
And RED means reverse engineering defense.
Oh, cool. Okay.
Okay. And if you look at this optimization problem, the constraint, if you look carefully, so we assume that we have a small set of clean examples available to us, much smaller than the training set size. So this small set it's completely useless for, say, training an AI from scratch.
Right. Right.
But it is useful. It's very useful for building a detector.
Right.
And again, this small set may be as small as 3%, 5% of the total training set size.
Gotcha.
Okay, it's not a large clean set.
Right.
And so so X belonging to D sub S means these are all examples that in the clean set that I know originate from class S.
Right.
And the one is an indicator function that says it outputs a 1 if the argument of the function is true.
Right.
And in this case, we're saying, well, when you add the putative backdoor pattern, the V, to X, does it induce the classifier F to decide to class T?
Okay.
And we want the fraction of samples from a given class S that get decided to class T to be large. Right. So we choose the threshold pi on the misclassification fraction to be, say, 0.9.
Right.
But actually, our detector will work with this is not, people talk about hyperparameters.
Right.
This is not really a hyperparameter because it works whether you choose pi to be 0.5, 0.9, 0.7. It really doesn't matter.
Gotcha.
Okay. And it also doesn't matter what norm you choose for D. We've played with the L1 norm, the L2 norm. It really doesn't matter.
And by the way, I think just for people who might not know, L1 would be absolute value differences between values and in the vector, and L2 would be squared. So kind of a squared error.
Squared and then square root.
Square root of n squared, yeah. So anyway, if you've heard mean squared error, That's L2. So anyway, yes. So continue on. So that's it. So pi in this case is not necessarily 3.14. It's actually just a value that you're putting in as a threshold.
That's right.
Yeah. Okay.
That's
Gotcha.
right. And now for people that are well versed in pattern recognition,
Right.
This constraint on the count of the misclassifications, this is not differentiable with respect to V.
Mm-hmm. Okay.
If you build a classifier, a natural training objective function you might want to choose is misclassification count.
Right.
You can't use misclassification counts if you want to do something called gradient-based learning.
Right.
Because the misclassification count has a derivative which is 0 almost everywhere.
Right. Right.
Okay. And we're going to use gradient-based optimization to estimate V. Okay. And so this is sort of an idealized formulation.
Right. Right.
And it kind of gives you a pretty good idea of what we're doing. But what we actually do is on the next slide.
Okay. Let me go over here. Sorry. There we go. Okay.
So we replace the misclassification counts by a surrogate objective function.
Okay.
And the surrogate objective, well, you're familiar with the perceptron.
Right.
Rosenblatt's perceptron, you can use lots of different objective functions. And similarly here, there are lots of good surrogates for misclassification count.
Right.
Let's focus on the first one, JST.
Okay.
Okay. So JST, we're summing over the patterns that ground truth come from class S.
Right.
We're summing up the deep neural network's class posterior probability for class T.
Okay.
Okay. And so if you maximize that objective over V, as you make this PT large, if the probability for class T becomes larger than for all other classes, you've induced a misclassification for that pattern.
Right. Yeah.
Okay. So it's pretty obvious that this is a good surrogate of misclassification count.
Gotcha.
Okay. And so we don't know whether there's a backdoor attack. We don't know which classes have been involved in the backdoor attack.
Right.
So we refer to the class of origin of a backdoor attack as the source class.
Yes. Okay.
So the source class would be dog, and the target class would be cat.
Right.
In the example that I gave.
Gotcha.
Okay. We don't know now. We don't know which classes are involved in the attack. So we do this optimization, maximizing JST.
Right.
For all class pairs.
Oh, wow. Okay.
Okay.
Yeah.
And so we do this for all class pairs, and then we get D of V for each class pair.
Right.
And so D of V, or actually we take the reciprocal, the inverse of D of V.
Okay.
If D of V is small, that would indicate if D of V is unusually small for a particular class pair relative to all the other class pairs.
That's something.
If it's an outlier, then that's the basis for making a detection. Now, we take the inverse because we want outliers to be large.
Right. Right.
So we take the inverse.
Gotcha.
Okay. These D of V's, one per class pair, these are detection statistics.
Right.
And we use these statistics both for learning a null model, that is a no attack model.
Right.
And for detecting outliers with respect to the null.
Gotcha.
Okay. Now, and how we even, if you go to the next slide, even how we do that is a novel contribution of this work.
Oh,
I'm not going to go over the flowchart here.
Right.
Fundamentally, what you should appreciate is that if I want to estimate a null distribution, and if some of the samples that I use in estimating a null are outliers,
right,
and I use them for estimating the null, I'm going to bias the null.
Yes, absolutely.
So we have a clever way of simultaneously using all these statistics, both for learning a null
Right.
and for assessing outliers with respect to the null.
Gotcha. Okay.
Okay. And those outliers are assessed by, if you're familiar with them, order statistic p-values.
Okay.
Okay.
Gotcha.
And pretty much that's all I want to say about this slide.
About that slide. Cool. All right.
Okay. So here, so this is not just an illustrative example. This is an actual example.
Okay.
We considered the CFAR10 image classification domain that involves 10 categories of images.
Right.
We use the chessboard pattern as the backdoor attack. Okay. And then we applied our reverse engineering optimization. And basically, our defense does three things.
Okay.
It says whether the classifier was backdoor attacked or not, yes or no.
Gotcha.
If there is a V that has an unusually large D inverse of, if there's a class pair with an unusually large D inverse of V,
right,
that class pair is detected as the backdoor class pair.
Okay.
And V is our estimate of the backdoor pattern.
Right. Which is very cool because you can see that down here that it reproduces the checkerboard mostly, not perfectly, but pretty close. So yeah.
Very close.
Yeah.
So when I first saw this pattern, and by the way, this was really, when you say it's a lot of work from the plane ride, I basically explained this idea to my student.
Right.
And within a few days, he showed me.
No way. Okay.
That we're reverse engineering the chessboard pattern solely on the basis of the DNN weights and a small clean set.
That is amazing.
So we were very excited about this.
Yeah. Yeah. Yeah.
We filed a provisional patent in 2019 for this method.
Right.
We have a U.S. patent on this method with a priority date of 2019.
Cool.
And this work appeared in online first in IEEE Transactions and Neural Networks and Learning Systems in December 2020.
Wow. That's really fast considering. Yeah. Okay. That's very impressive. Wow. Okay.
Yeah, we were excited about this. Next slide.
Yeah. There we go.
So we were excited about this, but we also recognized that there were limitations of this work. And for REDS in general.
Yeah.
Okay. So IPT RED was one of the very first post-training backdoor detectors.
Right.
There was another method that was contemporaneous with ours. It's called neural cleanse.
Okay.
These are both reverse engineering defenses.
Right.
So a problem with reverse engineering defenses is that they're based upon an assumption about how the attacker embedded the backdoor pattern into an image, into a sample.
Yeah.
Okay. As I mentioned, there are uncountably infinite possible embedding functions for digital attacks. Okay. And if your defense assumes a particular embedding function, and the attacker used a different one, this mismatch may very, very likely mean that your detector will fail.
Right.
It won't detect. Okay. And so we clearly saw the need for what we'll refer to as a universal detector.
Right.
One that is agnostic about the mechanism used by the attacker to embed the backdoor pattern into images.
Right. Right.
Okay.
Yep.
So more recently, in 2022, we came up with a universal detector.
Right. Yeah.
And that paper is to appear in the foremost security conference in the world.
Wow.
The IEEE Symposium on Security and Privacy.
Wow.
That will appear this year.
Wow. That's impressive. Yeah.
And that method is explained on the succeeding slides.
All right. So we get a little preview here, folks. There we go.
So actually, You know, actually, can we go back to
Sure.
the slide that shows backdoor patterns? The
Yeah.
very early slide that
Yep.
shows the backdoor pattern
Mm-hmm.
examples.
Yep.
So, okay, so look for example at either the dog image or the cat image.
Yeah, these guys over here.
Notice that the backdoor pattern is not destroying the image features that allow a human being, but also say an AI,
right,
in principle, to recognize what the scene represents.
Right.
So, in other words, the backdoor patch, it's not overlaid on top of the dog.
Right.
You can still clearly see the dog.
Right.
Okay. So the features that would normally allow you to recognize this as a dog are still there.
Right.
So how is it that the backdoor pattern wins out?
Yeah.
In fooling the classifier into thinking that this is, say, a cat or something else.
Right.
Okay. So that question inspired our universal detector.
Gotcha. Okay.
Basically, what we hypothesized is that since the regular features that would normally ensure that the classifier decides to the true class of origin,
right,
the fact that they're still there must mean somehow that greater weight is in the network is being given to the backdoor features.
Right. Right.
Okay. And we use the term overfitting.
Yeah. Yeah.
Basically, what's happening is the overfitting to the backdoor pattern is occurring.
And that's a key insight. I mean, that's like yeah.
It is and so the overfitting is allowing the backdoor features to overcome what we refer to as the source class discriminative features.
Right.
Okay. And there are different ways of mathematically quantifying overfitting.
Right.
The way that we did it, and I'm not saying this is a unique way of doing it. There could be variants of this. We used a measure of decision confidence.
Yes. Okay.
Okay. In particular, we refer to it as margin, but it's not exactly the margin that is the training objective function of a support vector machine.
Gotcha.
Okay. Basically, we look at the largest class probability produced by the network.
Right.
And the second largest probability produced by the network.
Right.
And we look at the difference.
Okay. So you're just throwing away all the noise, all the little guys, the probabilities. Yeah. Okay.
If that difference is very large, then you can say that the classifier is very confident in its decision making.
Right. Right.
And we associate overfitting with overconfidence.
Right. Yeah, this is really interesting. So just to back up, just in case people don't get this, when you do a classification, let's say CFAR, like 10 classes, it never says 100%. Like you as a human might go like, that's a dog. And you're like, I'm 100% confident that's a dog picture. But a computer never does that. It's like, I'm 92% confident. And there's a lot of little extras and there's a second most possible. But sometimes it goes down to like 51% versus 46%, something like that. So yeah.
Sometimes I never treat the softmax outputs of a deep neural network as true estimates of posterior class probabilities.
Okay. So do you look at the layer before then? Is that what you're actually looking at? Oh, okay.
No, we're looking at the softmax output. But what I'm saying is I would never think of the neural network's class posterior that it produces as reflective of true class probabilities. But it certainly is reflective of the confidence.
Yes.
In a classifier's decision making.
Right.
And so we use this difference between the largest probability and the second largest probability as we define that as margin.
Okay.
And we hypothesize that backdoor poison neural networks have a propensity for the existence of inputs to the network,
right,
that results in extremely confident decisions.
Okay.
Okay, and also we impugn rectified linear units as enabling such overfitting.
Right.
and I'll demonstrate that hypothesis, even about the Ray-Luz, is vindicated.
Okay.
So let's go to the next slide.
Yeah, and again, rectified linear units, that's just basically zero if it's less than zero and whatever the value is. So it can take an infinite amount of positive values, which means it can become very, very, very large, which is a problem when you're doing training because you can have explosion of some of the weights which dominate things, which is the insight. Yeah.
Exactly. So this hypothesis that we have translated into a formula is given on this slide. So here we're optimizing over the input space to the neural network.
Right.
We don't have in this. So now another advantage of this universal defense is that we don't need any clean examples.
Oh, wow.
What we do is we take the train network.
Right.
We solve an optimization problem, one per class, seeking an input pattern that induces the largest possible margin.
Right.
And notice for class T, we're looking at the difference between, say, the posterior for class T,
right,
and the posterior for the second largest class.
Right.
Okay. And we're optimizing over the input space, and again, this is done via gradient ascent.
Right.
Starting from a small random image.
Right.
Okay. And you might think, well, you have to do this optimization multiple times. In fact, no. We only have to do it once.
Wow.
For each class T.
Okay.
Okay.
Do you have to do when you say? Do you have to know what the attack pattern is or something like that? Or is that you're just looking for confidence? You don't care about anything else. It's just like, damn, this is a really confident category. So
this is why it's backdoor agnostic.
Yeah.
There's nothing in this formulation that assumes anything about the backdoor embedding function.
Right.
Okay. And so we do this optimization for every class treated as a target class of a backdoor attack.
Right.
And again, we use the resulting quantities, these what we'll refer to as maximum margins, as detection statistics, one per class. If you go to the next slide, the formulation, the approach is. Oh, I'm sorry. So on this slide, I'm showing you an illustrative example.
Okay.
Okay. So basically, our hypothesis is that the backdoor creates this susceptibility to producing unusually large margins, what we refer to as maximum margins.
Right.
Now, here I'm showing you an example. It's a toy example.
It's okay. It's good.
We considered two-dimensional data. Each class was a Gaussian mixture.
Okay.
Okay. Living in the plane.
Right.
Okay. And the backdoor attack in this case was a single Gaussian component added to class 3's mixture.
Oh, yeah. Well, there you go.
Okay. And here we're showing you the landscape, the margin landscape.
Right.
Of the backdoor poison classifier. And in the upper row panels, that's for what I refer to as the low poisoning rate.
Okay.
And in the lower panels, that's for the high poisoning rate.
Gotcha.
And class 3 is the backdoor target class.
Right.
And even for the low poisoning rate, it should be pretty clear that the maximum margin for class 3 is significantly larger than the maximum margins for classes 1 and 2.
Right.
Which were not the backdoor target classes.
Exactly. And this one's just out of control. So
that one sticks out like a sore thumb because the poisoning rate is 10 times higher.
Right. Right. But really
Okay.
interesting that even at a poisoning rate, is that 10%? Or is that just 10 samples out of your?
To be honest with you, I don't recall
Okay.
the numbers in
But it's
this
small.
example.
Yeah.
But still small.
Yeah. But it's still obvious, even from just looking at it, that, and certainly doing a statistical analysis of the classes, you would see that it would be like, bing. That's, yeah.
Yes.
All
So
right.
if you go to the next slide, so this is really just summarizing our approach. We solve this optimization problem, seeking the maximum margin for each class.
Right.
Then these maximum margins are detection statistics, and we're expecting that if one of them is unusually large relative to the others, that corresponds to a backdoor.
Right.
Again, we use an order statistic p-value, and in this case, I'm showing you the equation for the order statistic p-value.
Right.
Okay, and we make a detection, say, with statistical significance using we could use the common threshold of 0.05.
Right.
95% confidence.
Yeah.
But if we want to be more certain, we can use a more stringent threshold.
Okay.
Okay. And so this is our universal backdoor detector, UNIV-BD.
Wow.
Okay. If you go to the next slide, that should be showing a table of results.
Yeah. Yeah. Yeah.
So here we're comparing with a variety of other methods, a variety of other detectors. And we trained an ensemble of clean classifiers, and we trained an ensemble of backdoor poison classifiers, and for a variety of backdoor attacks with different embedding functions.
Right.
Additive, multiplicative, patch. There's something called a warping-based attack. There are many published attacks in the literature.
Okay.
Okay. And what you can see is that certain of these detectors, they work well on some attacks.
Yeah.
Again, when the attack is matched to the red assumption.
Right.
Okay. But then they fail on other backdoor attacks. UNIV-BD, it's not perfect, but it's overall the best, and by a significant margin.
Right.
Compared to the other methods. And also I should say that you should notice that these other detectors, they all assume availability of clean samples.
And also you have to throw at it what you expect the attack pattern to be as well, right? So that's too huge.
Well, but so for example, NC assumes a blended patch.
Yeah. Yeah, exactly. Right.
But it's being evaluated for attacks that are mismatched. It's not only being evaluated.
Okay. I got you.
Attacks. It's being evaluated for an array of attacks.
Right.
Okay. So our method doesn't require any clean data, unlike these other methods.
Right.
And it's by a significant margin the best overall method. And moreover, the clean column that corresponds to false positive rates.
Right.
So we do make a few false positives, but it's overall amongst the best in that measure as well.
Right.
Okay.
Right.
And we tried on a variety of image data sets here: CFAR 10, CFAR 100 that has 100 classes.
Right. Right.
Okay. Tiny ImageNet. I don't recall. Maybe Tiny ImageNet has 100 or 200 categories, something like that.
Right. Okay.
And GTSRB, I believe, is a sign data set.
Gotcha.
Traffic sign data set.
Gotcha. Okay. But still, I mean, those bold faces are most of the categories. You got the bold, the bold, so it's clearly a winner or tied for the lead with all these other categories. So yeah.
Right. So this is really demonstrating that the method is pretty much backdoor agnostic.
Right. Very
universal.
Impressive. Yeah.
Thank you.
I'm very impressed with this. This is, given the fact that it doesn't need all of this other information and and it doesn't need a clean data set because you never know if the supposedly clean data set has been poisoned as well. It's just, that's difficult. So yeah,
that's possible.
Yeah,
that's right.
Yeah.
And again, computationally, it's the lowest amongst all these detectors.
Yeah, by a lot.
And and in particular, if you look at something called META,
32 hours.
For CPOR-10 requires 32 hours.
Jeez.
For the larger data sets, you can't run it.
Right.
Forget about it.
Yeah. Yeah.
Okay.
Wow. I mean, but you know,
so,
you're looking at that 32 hours versus 27 seconds. So that's insane. Yeah.
Yeah. So one part of this work was detecting backdoors.
Right.
The other part was mitigating backdoors. And mitigating backdoors means post-training doing something to the train network to silence the learned backdoor mapping.
Right.
So that if the backdoor trigger is embedded in a test sample, it's no longer misclassified. Okay. So if you go to the next slide, I'll talk about how we mitigate. And this is also part of our S&P paper.
Okay.
That's to appear in 2024.
And obviously mitigation is very important because under normal circumstances, the inference engine just is out there and you might not have access to it to retrain it, or it might take a month to retrain it. You know, there could be a lot of reasons why you can't just go back in and retrain the data set or the inference engine. Yeah.
And in fact, actually, yeah, this is something that I forgot to tell you about at the beginning. So the post-training scenario in general,
right?
What motivates the post-training scenario? Well, imagine the following. Imagine you're the U.S. government.
Right.
You purchase a company's classifier.
Right.
Typically, that company is not giving you data rights.
No.
It doesn't give you access to the training set.
Right.
Okay. So all you have is a trained model.
Right.
And now you want to know, was this model infiltrated?
Right.
Okay. Consider apps on your cell phone.
Yeah.
That involve classification. Certainly you have no access to the training data. Okay. Also consider legacy systems. A system was built a decade ago. It works pretty well. People are still using it.
Right.
The data has long been forgotten. No one knows that they've lost access to the training set.
Right.
All of these scenarios motivate the post-training scenario.
Yeah. And also, I mean, and the mitigation scenario too, because it's great if you're like, wait, we detected it, but it's like, well, now we know we have a poison data set, but we can't do anything about it. So obviously step 2 is to mitigate.
You could throw it away. Right. But it may be costly, and time consuming, to rebuild a model. Yes. So our mitigation approach is really inspired by ideas from security. Right. I'm not a security expert. My colleague George is. Yeah. But you know, what are if you consider a computer system. What creates vulnerabilities in a computer system? Well, generally it's some kind of unnecessary functionality. Okay, maybe web services that you are using that are vulnerable. Right. Maybe certain port numbers. Yeah. That you shouldn't be allowing. Right. Okay. Vulnerabilities in computer systems are created by, let's say, unnecessary functionality. So what's unnecessary functionality? I claim it to be unnecessary functionality in an AI. Yeah. Well, go to the next slide.
All right. Oops, sorry. There we go. Here we go. Speaking of those, yeah.
So, now, of course, you need, I mean, some layers of your network could use linear activation functions, but obviously, in fact, I put this as an exam problem. If you exclusively have allow linear activation functions in your network, your network is just a linear map. Yep.
Yep.
And you know, if you call it a deep neural network with strictly linear layers,
Right.
you might as well just have one layer.
Yeah. Yeah. No, it's, I mean, that's the basic rule of any kind of neural network, is that you have to have a nonlinear layer somewhere. So yeah.
You have to have nonlinearities.
Yeah.
But why do you have to have ReLUs? So in fact, you know, and you kind of earmarked me in a certain way, which is correct. I joined the let's say the deep neural network bandwagon a little bit late.
Right.
And then I started looking, and I saw, well, people use ReLUs a lot,
Right.
and I couldn't find a paper that explained why. There are two obvious answers to this question. One is that the derivative is trivial to compute.
Yeah. Yeah.
And the fact that a ReLU does not have a saturation region,
Right,
means that you know, if you have a sigmoid, if you're in the saturation region, the derivative is basically zero.
right.
And learning becomes ponderous.
Yes, exactly. Yeah, you get that slowdown. So a sigmoid, folks, is that S curve. But also ReLUs are much faster to calculate than something like a sigmoid. And if you're doing it a billion times, you know, it's going to be a lot faster. So
yes, both the ReLU itself and its derivative.
Yes, yeah, both of them
are much faster to calculate.
Right.
That's correct. That's right. But the fact that this, for positive inputs, the output is unbounded.
Right.
This should be a bit troubling. Okay.
Yeah.
And basically, if so, imagine I have a backdoor pattern.
Right.
And there's a neuron that recognizes a backdoor pattern.
Right.
It outputs it pulses. It outputs a signal. That signal is conducted through a very large weight.
Right. Right.
And then you go into the next layer of ReLUs.
Right.
And that just propagates that large signal.
Right.
And then you can conduct through another extremely large weight.
Right.
Well, you can see how this is creating the large signals that induce the overfitting.
Yeah, exactly.
Okay.
And that just comes from the multiplicative nature of all of these layers. Well, I mean, if you have a sigmoid, it clamps it, so you can't really get that high. But with a ReLU, the value can become so large that it doesn't matter what anything else in the entire image is telling you, as long as that one weight is big enough that it just dominates everything, which can happen with a ReLU. Yeah.
Exactly.
Yeah.
And so this is a hypothesis that we had. And so we said, well, we want to mitigate the trained AI post-training.
Right.
How are we going to do that? Well, by clipping ReLUs.
Yeah. Yeah.
And optimizing over the clipping or saturation bounding levels on all the ReLUs in the network. Okay.
Gotcha. Yep.
So let's go to the next slide.
All right.
Okay. So for mitigation, we do assume access to a small, clean data set.
Mm-hmm. Okay.
We need access to a small, clean data set to mitigate.
Right.
Not to detect, but to mitigate.
Right.
Okay. We can go to the next slide.
All righty.
So this looks kind of complicated, but it's not that complicated.
Okay.
First of all, if you look at the equation GC bar,
mm-hmm.
So this is really just showing you, it's just the expression of a feed-forward neural network.
Right.
But where the ZIs, there's a Z vector per layer.
Right.
And the vector of values ZI are the clipping levels.
Okay.
That we're going to impose on the ReLUs.
Now, are the clipping levels learned by you? So you're actually training it to figure out what those levels need to be?
Well, you can see the formulation right below.
Yep.
So again, this is an idealized. In fact, I wouldn't even call this an idealized formulation.
Right.
This is sort of a rough idea of what we do, and then the next slide will show what we actually do.
Okay.
So here we're saying on the clean set, let's preserve the high classification accuracy on the clean set.
Okay.
So now pi doesn't correspond to a misclassification count. It corresponds to a correct classification count.
Oh, okay.
So we don't want to disrupt the functionality of the network.
Exactly.
On clean data.
Right.
But while keeping the functionality of the network on clean data, let's impose bounds on the ReLU activation functions.
Yeah.
And let's minimize let's minimize the sum of L2 bounds or squared L2 bounds on these saturation levels.
Yeah. Yeah. That's really cool though. And so you can effectively kind of learn from the clean data. You're like, don't need these values to be like these, explosive, exponentially big, well, not exponentially, but linearly large values. So yeah. Okay.
Now this is, and again, the indicator function is not differentiable.
Yeah. Yeah.
So we don't do this.
Okay. Right.
But we also don't do this for another reason. Okay. Our actual objective function is on the next slide.
Okay. And let's take a look at that. Okay. Aha.
So here, there are two terms.
Right.
Let's focus on the second term first. The second term with a Lagrange multiplier lambda is penalizing the maximum margins.
Okay.
And here we don't just penalize one maximum margin because maybe there are multiple maximum margins.
Right.
There might be a landscape with multiple unusually large margins, and we want to tamp them down.
Right.
Okay. And that's what the second term is doing. And so we're optimizing these clipping levels on the ReLUs in order to tamp down two large maximum margins.
Right.
That's what the second term is doing. What's the first term doing? The first term, rather than trying to have a surrogate measure for classification accuracy, we came up with the following hypothesis. We said on the clean, the backdoor is affecting input patterns that contain the backdoor trigger.
Right.
But we hypothesized that the backdoor is not affecting the output for clean patterns.
Yes. Okay.
So FC is the logit. It's the class logit for class C.
Okay.
For the network that has ReLUs without clipping.
Right. Right.
And we hypothesized that for these clean examples, that this logit value is correct, essentially.
Yeah. Yeah.
So we treat it as real valued supervision.
Oh yeah. Okay. Right.
And so we optimize over the clipping levels for the bounded network F bar, the logit for the bounded network from class C, F bar C, to agree with the unbounded network's logit values on the clean samples.
Right. Yeah. Okay.
And this is real valued supervision.
Right.
Real valued supervision is contains much more information actually.
Right.
Than class label supervision.
Yeah.
Especially if that supervision is correct.
Yeah. 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 Okay.
Which we hypothesize it to be.
Right. Wow, that's fascinating. And probably it converges very quickly in that case too, because of the nature of the fact that you can do regression on it. So
it's a gradient based optimization.
Yeah, yeah.
But it's not and how much computation this takes is a function of the size of the clean set.
Yeah, yeah, okay.
If the clean set is small,
right? And
so this optimization, it's dramatically dwarfed by the training time.
Right, right.
And I would say, even if it was a significant fraction of the training time,
right?
If it results in a mitigated classifier,
yeah.
You would be satisfied with that.
Oh yeah, for sure. Exactly.
Yeah.
Especially again under circumstances where you don't have access to, a lot of the original stuff. You're not allowed to retrain it for whatever reason. So yeah. That's very cool.
So
right.
this block diagram is just, again, emphasizing that we're replacing ReLUs by clipped ReLUs
Right.
with the clipping values optimized based upon the objective function on the previous slide.
Right. Yeah, the big change being down here with the bold-faced line no longer is an unbounded ReLU. It actually is clipped somewhere, and that's a learned thing. So, yeah.
And it's clipped post-training.
Yeah, yeah, which is super cool.
And let's go to the next slide.
All right.
So here we're showing results, and this is a busy slide. I don't know if you can blow it up.
Sure. Which part do you want me to blow up? Because eventually I'm going to run out.
Just increase the size a little bit.
Yeah.
So there are 3 performance measures.
Yeah.
Accuracy is the accuracy on a clean test set.
Okay.
Of a trained classifier.
Gotcha.
Okay. Attack success rate is the frequency with which, when you embed the backdoor trigger in a test sample, that test sample is misclassified to the target class of the attack.
Right.
Okay. And PACC is the accuracy of with which the accuracy of the classifier on a test sample with the backdoor trigger.
Right. Right.
Okay. And so if you look at in the row without defense.
Yeah, that's pretty bad. Pretty stark.
If you look at the clean accuracy, so this is CFAR 10, the clean accuracy is about 91%.
Right. Down here.
For all these different attacks.
Right.
Okay. The attack success rate is very high, well above 90% for all these attacks. And the accuracy on the trigger examples, as you would expect, I mean, since the trigger is causing misclassifications, the true class is not being decided in almost all cases.
Right.
So the PACC is also very low without defense.
Yeah.
And so all these other rows are showing the results for various mitigation methods.
Right.
And our mitigation method is at the bottom. The one that I just described is at the bottom. And you can see, if you look at accuracy, clipping does reduce the accuracy modestly.
Yes, yes.
Say 91% to 89%.
Right.
Okay. So there is a little footprint on the classification accuracy, on the clean classification accuracy.
Right.
But look at the attack success rate.
Yeah.
it was close to 100%. Now it's less, in all cases, it's less than 4%.
Right. Right.
Okay.
Yeah, that's impressive.
So the attack has been silenced.
Yeah. Yeah.
And on examples with the trigger, in most cases, for most of these attacks, they're being classified to the true class.
Right.
Post mitigation. And again, if we compare with other methods, although I'm not bolding to indicate it, if you eyeball this, you'll see that our method is overall the best.
Yeah. Yeah.
And significantly better than most of these defenses.
Yeah, I was going to say sometimes like drastically better. So yeah.
And moreover, while requiring far fewer clean examples than most of these other defenses as well.
Gotcha. Is that what the number of images is here? Like you're only using 50 images to train on?
So N image is the number of clean images per class.
Yeah. Okay. Gotcha.
So we're using 50 clean images per class.
Right.
Whereas the training set had 5,000 clean images per class.
Right.
The NeuroCleanse mitigation method it's requiring 500 clean images per class.
Right. And doing much, much worse. So yeah. Yeah.
Okay. Yes.
And also I noticed that the mitigation strategy has had a harder hit on the actual, even for a clean data set, it's affecting it significantly more than yours. So
for some defenses more than others.
Right. Yeah. Like this one for Juanet. Yeah. Yep.
Yes.
Cool. Wow. So
this is all in our security and privacy paper.
Right. Right.
Univ BD and Univ MB, mitigation of backdoors.
Gotcha. Cool.
Okay. Now, we also did the following. We said, well, okay, we have a method inspired. We hypothesize that backdoors are an overfitting phenomenon.
Mm-hmm.
We know that there are other overfitting phenomena.
Mm-hmm. Absolutely.
Overtraining is an overfitting phenomenon.
Right.
And class imbalance, highly skewed classes, is a significant source of overfitting.
Right.
So in other words, if I have one class which is very common
mm-hmm.
and another class which is very rare, and I train a classifier on a data set, with this high class imbalance,
right,
the accuracy on the common class will be very high.
Yes.
It's possible that the classifier will never classify to the rare category.
Right. Right.
Okay. The accuracy on the rare category will be very low. It could even be zero.
Yeah. Yeah.
Okay. So we said, well, okay, inspired by our ideas from backdoors,
right?
Maybe we can more generally mitigate overfitting post training.
Nice. Yeah.
That has a non-malicious cause.
Right. Right.
Okay. In particular, class imbalance.
Yeah. Okay.
So here, the first term is the standard cross entropy loss
mm-hmm.
is used for training a classifier.
Right.
The second term is again pretty much the same as it was before. It's we're trying to suppress overconfidence.
Right. Right.
These maximum margins. Okay. And this is post-training fine-tuning.
That's amazing.
Using a small, clean data set D.
Right. Right.
Okay. And this work has not been published yet. It's on the archive. It's under review.
Right.
IEEE transactions on AI.
Yeah. Yeah.
Okay. If you go to the next slide.
Mm-hmm. This, by the way, is really cool. Just to stop on this too, another place I could see the usefulness of this would be recurrent neural networks and the like, where you're having multiple layers that are being multiplied through time. So you always have that exploding gradient problem, and this would really mitigate something like that. Yeah.
No, but just to mention, by the way, even like, say, for example, IPT-RED.
Mm-hmm.
IPT-RED works whether the network is feed-forward or recurrent.
Right. Oh, wow. Okay.
I had a master's thesis student that demonstrated that the same defense works on LSTMs, on recurrent neural nets.
Yeah. Okay. Yeah, but I even mean like without the malicious intent, a lot of times when you train those things, what happens is something just goes and it just takes over. Yeah, through the multiplication of the layers. Yeah.
Instability.
Yeah, exactly. So this is really cool to do. I've often thought about clamping ReLUs, but I was like, how do you know what the number is, the magic number? But what you've got is a way to train that to figure out what that magic number is. So yeah. All right.
Yes. So here we took CFAR and we created an imbalanced version of CFAR.
Okay.
CFAR has balanced classes, but we only allowed 200 examples for the bird and truck category in the training set.
Gotcha.
And all other classes have 5,000 training samples.
Right.
And you can see that with regular training, the overall accuracy is 84%, about 85%.
Right.
For the bird and truck categories, the accuracies are low.
Yeah. Yeah.
Okay. And after applying our post-training mitigation by optimizing that objective that I showed you on the previous slide,
right,
the accuracy for bird goes from 34% to 72%.
Yeah.
The accuracy for truck goes from 67% to 90%.
Which is actually better than the general average. So that's really cool.
Yeah. So, this is really a demonstration that judicious selection of ideas from inspired by adversarial learning,
right,
can improve AI robustness.
Yeah. Yeah. That's really cool. Wow. All right. Oops.
Yeah.
Let's shrink this down a little bit here.
So, large language models, of course, they're of tremendous interest these days. I can't talk at length about them because this is work that we're doing right now.
There we go.
We're doing experiments on this right now.
Gotcha.
But so large language models, of course, are generative. They're not classifiers.
Right.
But the response of an LLM may be consistent with binary sentiment, positive or negative. It may be consistent with whether the output is being censored or not.
Right. Yeah.
Again, that's binary, 2-class. And moreover, I may query an LLM with is it the case that such and such is factual?
Yeah.
And then its response, its binary response is again really categorical.
Right.
Okay. So ideas that we've demonstrated pervasively work for classifiers, we believe, will also work for LLMs.
Wow.
Okay. Now LLMs are trained on for example, an image of the web.
Right.
So that's an insecure data supply chain.
Oh yeah.
And moreover, when you do reinforcement learning with human feedback, if even one worker is adversarial,
yes,
this can inject a backdoor into the model.
Yeah, there's been a lot of research recently, even unintentionally, just a little bit, just a couple % of incorrectly labeled or otherwise incorrect data can completely blow up a training run. So yeah,
a training run or a fine tuning run.
Yeah.
If you fine tune, even if the poison set is a small fraction of like the fine tuning set itself,
right?
Again, a key idea in this work that I'm in the talk that I'm presenting here,
right,
is that even if the backdoor poisoning rate is low,
right,
that pattern it's essentially consistent.
Yeah.
So it creates this very clean signal that can be recognized by the network.
Right.
Whereas the features in normal examples, there may be quite a bit of variability in them.
Right.
And so that signal is not as, let's say, deterministic.
Yeah.
Relative to the backdoor signal.
Right.
Okay.
Yeah. Okay. That's really fascinating. Just like it's like once you say that, it's so obvious, but it's like one of those things where it really takes a while to get to the point where you realize that it's like, yeah, it's a deterministic signal that you're providing with this malicious attack.
Essentially. And the realization of this too, I mean, of course, I've been working in this area for about 8 years.
Right.
So this is accumulated knowledge over quite a long time.
Right. Very interesting. All right. So let's see. I don't know. You want to talk about some of these images down here, or
if you want, if we have time, if you want me to.
What do we got?
It's up to you.
TTEs are. Sorry, I'm just trying to.
TTEs are actually the first adversarial attack that became very glossy, very. So TTEs are what people refer to also as adversarial inputs. They don't involve poisoning.
Yeah.
They involve taking an input pattern and perturbing it, so you push it across the decision boundary.
Right.
Okay. And that's done via an optimization problem. Using something like, for example, you could just use the probability, the class posterior for the target class of the attack.
Right.
Modify the input pattern to increase that probability.
Right.
Until you push the pattern across the decision boundary from the starting class S to the target class T.
Right.
Okay. This was the first kind of attack that got a lot of publicity.
Right.
And the thing, and the ability to push a pattern across the decision boundary, I mean, for someone that works in this area, it's like, well, this is trivial. It's completely obvious.
Yeah.
The 2014 paper that first talked about adversarial inputs.
Mm-hmm.
I think its real contribution was saying, hey, for images, you can do this while not changing the decision that a human being would make.
Right.
So you can do this in an imperceptible way.
Yeah.
And in fact, in some sense, you can kind of argue that this is a demonstration that AI is not really there.
Yes.
Yet.
Yes.
Because if you can fool if this thing still looks like a cat,
Right.
and the classifier says it's a dog,
Right.
and a human being is not fooled,
Right. Yeah.
well,
there's still room to go.
There's still work to do
Right.
to improve AIs.
Gotcha.
Okay. So,
we have some examples here. So yeah, there we go. Exactly.
Yeah. So, in the upper row, you're seeing test time evasion attacks using different kinds of different attacks. One is called FGSM.
Right.
One is called CW. These are famous attacks. They're very well known. Now, and on the left, you see the original image, which is a digit of a 7.
Right.
And you can see, you can see changes that have been made to the image. So, digits are basically black and white.
Right.
The attack is not going to be imperceptible.
Right.
If you have white on black background.
Yeah.
But the changes are still, they're fairly subtle.
Yeah.
Okay.
Well, certainly we as human beings would not have any problem still recognizing all of those as 7s and all of the below images as ships. So yeah.
But if you see the background for the FGSM attack, or even for the CW attack with the distortion of the image,
right,
you might imagine that you might say, yeah, this is certainly a 7, but it might have been tampered with.
Yeah, noticeable.
Okay.
Right.
But if you look at the bode images,
right,
the attack is largely imperceptible.
Right. Yeah, the FGSM is the one that you can kind of distinctly see because there's a patterning back there, but the other two are very imperceptible in an image like that.
Yes.
So, yeah.
So we wanted to. So we've developed several detectors of TTEs.
Okay.
And one of them is again inspired by adversarial learning. Okay. And in particular by GANs.
Yeah.
So GANs, what is a GANs? A GANs is a generative model.
Right.
And how is it trained? Well, you have two models. One is called the generator, another is called the discriminator.
Right.
The generator takes you have some domain that you're trying to generate. Say we want to generate images of dogs. Say.
Right.
The generator takes a random input and tries its darndest to convert that random input into an image of a dog.
Right. This, by the way, for folks, before diffusion models was state of the art for image generation. So,
right, exactly. And the discriminator has examples of dogs, and it takes examples of dogs and examples produced by the generator, and it tries to distinguish the two.
Right.
To accurately discriminate the two. And you have this interplay, this adversarial interplay between these two models, the generator and the discriminator. Okay. And this interplay in a game theoretic optimization setting, minimax optimization,
right,
results in generators that have decent fidelity in producing things that look like like the real deal.
Okay. But also, interestingly enough, the discriminator becomes quite good too over time. So
it does, but in the original applications of GANs, I think you just throw it away.
Yeah.
Which that I was like, well, okay, do you have to throw it away? When reading the original paper,
there you go. Yeah.
And also there's a mode collapse problem with GANs.
Mm-hmm. Yeah, definitely.
Which, if you look at the objective function, it seems pretty obvious to me that mode collapse is not penalized in any way by the objective function.
Right.
Okay. But if you think about it, what the generator is producing is kind of like an adversarial input.
Yeah, absolutely.
And so we said, well, okay, let's consider GANs, and we'll train them, and we'll take the discriminator.
Right. And
we'll use the discriminator as a detector of adversarial inputs, of TTEs. Mm-hmm. And in this example, and we use a particular GANs, which is called an AC GAN, which is class conditional. Mm-hmm. Mm-hmm. So you have an image in this example. It's a clean image of a 6.
Right.
The deep neural network is deciding that this is a 6.
Right.
the discriminator outputs two values. One is the a class posterior,
Right.
and it's very confident that this is a 6.
Yes. Yes.
And it also outputs another probability, which is the probability that that this input is real, legitimate, or real.
Right.
And that value is fairly high.
Right. Right.
And then for the output of the generator, conditioned on the fact that this is a 6 and given a random input,
Right.
you can optimize over the random inputs, or over input space. You can optimize over the inputs to find the closest, the input that leads to an output from the generator that's as close as possible to the input image, to the original image.
Right. Right.
Okay. And the reconstruction loss is very small.
Yeah.
Okay.
Yeah.
So in principle, the outputs of the discriminator and the reconstruction loss of the generator can be used as detection statistics.
Right. Right.
And in this example, we would say this is not an adversarial input.
Right.
The discriminator's output's high, the reconstruction loss is low.
Right.
But now, if you see the attacked image,
Yeah.
it's decided as a 7.
Mm-hmm.
The discriminator is saying that, well, okay, the probability that this is a 7 is low.
Right. Right.
And the probability this is real is very low.
Yeah. Basically nothing.
Okay.
So,
and the reconstruction loss is high.
Right.
Because the generator is trying to produce a 7 that's as close as possible to a 6.
Right.
And it can't do a very good job of that.
Right. Right.
Okay.
Fascinating.
So
Yeah.
we proposed a test time evasion detector based upon a type of GANs.
Right.
And if you go now, and in principle, you can use the output of the generator and the discriminator.
Right.
But because of the mode collapse problem, we found that the generator is not very reliable.
Okay.
But the discriminator is very reliable.
Yeah, I mean, you really don't even need it because these values are clearly so drastically proving that, that it's not.
This is an John. This is an illustrated.
Yeah. But I'm just saying. So yeah. Cool.
Yeah. So if you go to the next slide, so here we're looking at receiver operating characteristic area under the curves for false positive rates up to 0.2.
Right. Right.
So the maximum possible perfect performance would be a partial AUC that's 0.2.
Right.
Okay. And we compared our method, and in particular, let's just look at DAD. That's the discriminator-based AD based upon the GANs.
Right. Right.
And you can see, and so perfect would be 0.2.
Yeah. Yeah.
And our area under the curves are almost all above 0.19.
Right.
So this is very good detection accuracy.
Yeah.
And much better than a variety of other detectors.
Right. Yeah, very impressive. That's that's really cool and such an interesting way to reuse GANs. And it's that I think it kind of circles back where we were talking at the beginning before we really got into this about the old school way of doing AI versus the new school way. But GANs as of 2020 or so became old hat. But now it's like, look at this. They're still incredibly useful. So yeah.
Yes. And
just real quick before I let this go, I'm just going to throw this up quick in case people want to see some references. So you guys can, pause the screen and take a look at that if you're interested.
So the TT detector is published it was published last year in Computers and Security.
Gotcha. Very cool.
Yeah.
So let me switch back to both of us here again. Wow, that was my brain isn't like a wet noodle from like getting all that information. It's just fascinating, and I hope people understand this is pretty impressive stuff. This is cutting edge research. This is being published in very high end journals and being presented at high end conferences. So this is like the real deal, folks.
Well, that's kind of you, John, and
it is.
and I want to thank you for inviting me.
Yeah. So let's just take 1 second before we end here. Why? Okay, there's a lot of math, a lot of stuff going on here. Why would I, as the normal human being, care about any of this? Right? This is AI research. What do we care? How does it affect a normal person, or could it affect a normal person?
Well, I think you said it at the outset. there's been an explosion of interest in this area.
Right.
And whether we like it or not, it seems that models like ChatGPT are here to stay.
Right.
And people may rely on them.
Yeah.
And if they're insecure or simply unreliable, there's a need to improve them.
Okay.
Okay.
That's pretty good. It's pretty reasonable. The more we become to depend on these things, the more important it is that we can trust them.
Right. And you know, in certain industries, the trust is not there yet.
Yeah.
But they are starting to make inroads, even into we'll say high risk industries.
Right. Right.
Okay. So that's why people should care about this and support this research.
Yeah, there we go. Support this research. Support your local university and your AI researchers. So there you go. Well, thank you so much, David. I mean, this was fascinating. I learned a ton. I'm sure everybody else learned a ton too. And we really appreciate your being here. And I would love to talk to you. I really want to talk to you about alignment one of these days also. And I know that's not your specific area, but let's just set aside another conversation to just, you know, we can more broadly talk about alignment and the issues with AI alignment and everything. But in the meantime, thank you so much for being here. And everybody, I'll leave David's contact info in the description. So if you want to email him or something like that, you can do so. And thank you so much. And everybody have a great day. Bye-bye.
Thanks, Dr. Know-It-All.